In a previous video, I implied that the acceleration of an object sliding down a frictionless surface set at an angle theta above the horizontal was the acceleration due to gravity g times sine of that angle. Now, as an example, we want to use Newton's second law to derive that expression. First, we're going to start with a picture. Here's our object sliding down a frictionless surface set at an angle theta. If we want to apply Newton's second law, the first thing we have to do is identify an object and all the forces on that object. Well, our object is obvious enough. We want the block. And what are the forces on this object? Well, there's gravity, and there's anything that crosses that barrier surrounding the object. And the only thing that is a contact force that the surface exerts on the block. It's frictionless, so that means there's no component of the force tangential to the surface, so the contact force only exists perpendicular to that surface. So now we want a free body diagram, and when I have an inclined plane problem, I always set up two sets of axes. One set that is parallel and perpendicular to the ground, which is gray in this picture, and another set that is parallel and perpendicular to the surface, which in this picture is pink. Then I want to find the angle that I'm given in the problem and find out where that angle is on my axes. This angle is equal to this one here. And now, due to geometry, I know that every other angle is exactly that angle theta. That's going to help me find components when I set up my free body diagram. Now I get my forces on my free body diagram. My first force is gravity, and I know, given the gravity model, that that points to the surface of the Earth straight down, so that's going to be along that gray axis. The second force is a contact force, which I know is perpendicular to the surface, so that points along the pink axis. I need a coordinate system, and I've decided to set my coordinate system along the pink axes, the ones that are parallel and perpendicular to the surface, because I know the motion is constrained to move along the surface, and so I'd like my x-axis to be along the one-dimensional motion of the object. If a lot of this looks confusing and you haven't been doing this a long time, sometimes I like to simply put plus x, plus y, and minus y on all the different axes, so it's clear to me what my primary axes are and which one is positive and negative. All right, I'm ready to apply Newton's second law. Newton's second law says the vector sum of all the forces on an object is equal to the mass of that one object times the acceleration of that object. So I've written that vector sum here. I like to write it vertically because it helps me extract scalar relationships later when I write out the vectors in component form. So first, the force due to gravity. I need to find the x and y components. Note that since my x and y axes are along the incline, the force due to gravity does not lie along the axis, so I'm going to have to find its components. To find the components of a vector, I draw a line from the tip of that vector to one of the axes such that it creates a right angle. And now I have a right triangle. The magnitude of the vector is the hypotenuse of that triangle. So then I can find the lengths of that triangle, and those will be the magnitudes of the components. So the length of that side, if the magnitude is the hypotenuse, will be the x component. And the length of the other side will be the magnitude of the y component. And then I look at the direction of the coordinate system to determine the signs. So what is the x component? Well, I know this angle, which I've determined earlier, is the same as this angle. So the x component is the magnitude of the gravitational force times sine theta, since this side is opposite the angle theta in this triangle. And now I want to know, is it positive or negative? Note that this length is on the positive side of the vertical axes, so thus the component is positive. Now let's look at the y component. The length of that side is the hypotenuse times cosine theta, since it's adjacent to the angle. Is it positive or negative? It is certainly on the negative side of the y-axis, so that's a negative component. So I use trigonometry to find the values of the components, and I always use the picture of the free body diagram to determine the signs. Well, what about the contact force? Well, it lies along the y-axis, so its x component is 0. Its y component is then the magnitude of the force, and it is certainly on the positive side of the y-axis. Now this is equal to the mass times the acceleration, and the x component is the mass times the x component of the acceleration, and the y component is the mass times the y component of the acceleration. Now I can easily extract scalar equations from this vector relationship that I can use to solve. The x component gives me the force due to gravity, the magnitude of the force due to gravity sine theta is equal to the mass times the x component of the acceleration, and the y components give me that the contact force minus the magnitude of the force due to gravity times cosine theta is equal to the mass times the acceleration in the y dimension. Now going back to my problem, what sort of information can I extract from the context of the problem? Well, first of all, I know that the acceleration along the y-axis is equal to 0. I set that up when I established my coordinate system. All of the movement is along the x-axis. And of course, from my model of gravity, I know that the magnitude of the force due to gravity is the mass of the object times g, the acceleration due to gravity. Putting in 0 for the acceleration along the y-axis, I find that the magnitude of the contact force is equal to mg cosine theta. I wasn't asked to solve that, but in some problems I might need to know that information. Does that make sense? It does. The contact force is equal to the y component of the force due to gravity. And because those magnitudes are equal is why there's no acceleration in the y dimension. The x dimension is what I'm interested in, of course, and that tells me that the mass times g sine theta is equal to the mass times the acceleration. The masses then cancel out, and I get the acceleration due to gravity down a frictionless incline is g, the free fall acceleration due to gravity, times sine theta, where theta here is defined to be the angle between the incline and the horizontal. Does this make sense? It does, because as theta goes to 0, then the acceleration goes to 0. It won't be moving if the incline is flat. Where if theta goes to 90 degrees, you now have free fall. The acceleration is just g.